Today we are going to learn about rotation and energy. You already learnt about moment of inertia, right? So let us look at questions that you are going to first try and solve. For example, if I now look at this disk, and if I think of this as the axle of the disk, this is the axis here, and if I let go, there are these two blocks, right? So these two blocks are going to pull it down. Now you have done these problems when this was a massless disk. Now this disk has a mass. It also has a distribution, so it has moment of inertia. Okay, so if I now release it, what is going to happen? It is going to start rotating. Now of course this is not the first problem that we are going to solve. So we will get to these kinds of problems. We will start with easier problems first. Okay, so let us take a case where I have something like this, and if I release it, you can see that it is going to rotate. We will assume that there is no loss in energy. So if I leave it here, you can see that when it gets to this point, does it have a velocity? Yes, angular velocity, right? And you can see that if I make it go around, that is reasonably straightforward. You know how to calculate its kinetic energy. So let us look at its kinetic energy in a little bit more detail. So we are going to look at first problems where the axis is fixed and there is just one object, not like the other one that we saw where there were multiple objects that were moving. So we are going to first deal with the simpler case. One object, I just release it and it is going to come down. The question will be, at this point, what is its angular velocity? So to do that, we are going to use this idea of energy, and energy when an object is rotating. So let me take this guy here and let us draw this object. So let me say that I have this object like that. Okay, so this is the object that we have here. And this point is going to be our axis. So this object is going to rotate about that axis. So suppose I decide to place this here. Suppose I leave it here, right? Now if I let it go, you can see that it obviously comes down with a velocity, right? At any instant, let us say that it has a velocity. Now, what kind of velocity will you talk about? Will you talk about the same velocity for every object, every point on this object? No, right? Because clearly this point is going to move, it's going to basically cover a much larger circle. This point D is going to cover a much smaller circle. So clearly all of them have different speeds, but all of them have the same angular velocity. Okay, so if I took this point and let us say that this distance was R1. So this is my axis, I'll call it A, and let's take this point, let's call that B, and let's say I have a mass m1 there. What is the velocity of this m1? What speed does it have? Forget velocity, what speed does it have? Well, if it's going to rotate in this direction, let's say that was omega, then it's going to have a speed that is in this direction. You can see that. If I hold it here and look at this object, look at how it's moving. It is moving like this. Can you see that that is the direction in which it's moving? Right? So this is the direction it's moving. You already know that this must be R1 omega. Now I have taken a nice and laminar object, right? What if I took a nice big pumpkin and I rotate it? Then what is going to happen? You will have points all over. You will have points, it's a three-dimensional object, so you will have points all over. But when it is rotating, you will still see that this point relative to the axis, suppose I took that as my distance. So let us say that this was my axis. So from around my axis, it's going to go around like that. So it will also have a velocity which will be dependent on the distance, R, whatever, R1, R2, R3 into omega, but it will be in that direction. So the velocity is perpendicular to this radius, and the value of the velocity is, magnitude of the velocity is R1 omega. So I hope that is clear to everybody. Okay, now what is the kinetic energy of this little fellow here? What is the kinetic energy of B? Half m1 v square, right? Half mv square is the kinetic energy. But what is v here? R1 omega. So it is R1 square omega square. That is the kinetic energy of the first particle. So I'm going to write that as kinetic energy 1. Okay, now if I took another particle, let us take a particle here, let's call that particle C, and if I join it, okay, so what I'm going to see is, let me call this R2. What will be its velocity in this direction? It is going to be R2 omega, that is the magnitude. And let us say that its mass was m2. So what is its kinetic energy? Kinetic energy of the second object is half m2 r2 square omega square. right? So now you can do this. You can now imagine that I have a third particle, a fourth particle, a fifth particle, sixth particle. All of that makes up this entire object. So this object is actually a bunch of particles. Well, this is a continuous object, so it's infinite number of particles. But for us, it really doesn't matter. So if I did this continuously and I added this all up, you can see that the half is common and you are really only adding up the m1r1 square, m2r2 square and so on. So this total kinetic energy, this is the total kinetic energy of the entire object, every particle's kinetic energy put together, and that is half. This is the summation m1r1 square, m2r2 square, right? m1r1 square plus m2r2 square, etc. into omega square. And this thing that you are looking at here is what we have called moment of inertia. The reason we spend so much time calculating it so that we can calculate kinetic energy easily. So the total kinetic energy is nothing but half I omega square. Now this I has to be about the axis. So I'm going to write IA. IA as in IA for the axis. Moment of inertia about the axis A, passing through A. So I hope that is clear. Does A have to be the center of mass of this whole body? Not required. You look at this. Do you think this is the center of mass? No, right? This was not the center of mass. In fact, this need not even be on the body. Sometimes I can have a case where this object is rotating like this. You may be wondering how is that possible, right? But if you take the moon is going around the earth. Now where is the axis of the moon? Actually through the earth. But the moon is not on the earth. So the moon's axis, if you want to think of, is around the earth. So basically the whole object is going like that. So the axis is here, but the object is there. So it's absolutely fine. All I'm asking you to do is to calculate moment of inertia about A, and then you do half I into omega square. So I hope that part is clear to everybody, right? So let us just take a couple of simple examples and then apply this idea. Okay. So suppose I tell you that I have a rod. Let's take this rod. And if I tell you that this rod is rotating with some omega like this. Okay, I don't want to hurt myself. So let us say that it's going around like this. Okay, so keep that as a fixed axis system. And let us say that it's rotating at a constant angular velocity. You can also see that with a rod like this. So let us say that it was rotating. And at this point, I just want to calculate what its moment of inertia would be first. So it is going to rotate like this. Now I'm not talking about allowing it to fall. Okay, because there then the question becomes a little bit more tricky. So this is just a plain rod. Let us say has length L, which is 3 meters, has mass which is, let us say, let me call it capital M, has a mass of 2 kilograms. And let us say it is rotating with an omega which is 3 radians per second. Okay, what is the kinetic energy of this object then? Kinetic energy will be half I omega square. Now the omega square part is 9. Now what is I for this thing about this axis? You know the formula, ml square by 3. ml square by 3. So this is m, which is 2, l square, which is 9 by 3. Okay, so now if I try to calculate this, you can see that I can cancel this out. And so that is 3 into 9, 27 joules. As long as I use SI units, the whole thing will be in joules. Okay, moment of inertia has an m, kilogram, meter square. And then this one is radians per second square. So it has meter square by second square, which will give me V square. So it will be basically joules, kinetic energy. Now this kinetic energy is the kinetic energy of the entire rod. You will later learn another formula where you can look at kinetic energy of rotation about the center of mass plus the kinetic energy of the center of mass. Now that kind of a formula we are not using right now. This is fixed axis. So we are only focused on fixed axis. What does that mean? The axis isn't moving. Now the axis can be anywhere. It need not be through the center of mass, but it has to be fixed. So I hope that was clear to everyone. So you can calculate how to calculate energy. Very straightforward and simple. Now suppose I have a disk. And this disk is rotating about its axis here. Let us say with an omega of 2 radians per second. Okay, so the disc is going around like that. Let me say that the mass of the disc is 5 kg and the radius of this disc is, let us say, 40 centimeters. Okay, so it has a radius of 40 centimeters. What will be its kinetic energy? Half I omega square. So kinetic energy is going to be half I, so leave the space for I, omega square is 4. Okay, now if I take this, what is the I for a disk about the center? mr square by 2. You remember that? So therefore this is m into r square. Remember that this is 40 centimeters. You have to use it in SI units. So it is 0.4. So 0.4 into 0.4. 0.4 square by 2. mr square by 2. So if I now try to calculate this 2 will basically go away, the 4. 2 and 4 will go away. So this is going to give me 4 into 0.5. This is going to give us 2. So this whole thing is going to give me 0.8 joules. Is that okay? So now let us take this. So if I look at a disk that is going around like this axis is fixed. This 0.8 joules is for the entire disk. It doesn't matter whether the disk was rotating like this or whether the disk was rotating like this. The axis has to be fixed and relative to the axis, this is how it is rotating. Correct? I mean, if this is the axis, obviously, this is how it is rotating. And so you do just simply calculate half I omega square. Will it be the same answer if this guy was rotating like this? If this was the axis? No, right? You'll have to calculate the I for that axis. So I hope the basic idea of how to calculate the kinetic energy is clear. Now if I took the same disk and I decided that instead of keeping this as the axis, I'll keep this as the axis and then let it go around like that, then you can have the same omega, you can have the same mass, you can have everything the same except the axis is this point. So now let us calculate again. So if I keep it here and make this fellow go around like that, notice that every object is moving faster, not every point, but the whole object overall. You can think of the center of mass moving, everything is moving, all these parts are moving faster than they were earlier. Because when they are here, they are only moving like this. Whereas when they are here with this as the pivot, you can see that that thing is moving faster. So obviously expect the kinetic energy to be more. We can calculate. I'm going to assume it is the same. So this is the same omega. Okay, in this case it was going this way. Now I'm saying it's going that way. 2 radians per second. This r is 0.4 meters, 40 centimeters, and this is 5 kilogram. I have to do kinetic energy is half I omega square, half, what is the I that I'm going to calculate? Omega square is simple, it is 4. It is a scalar quantity, very, very easy to calculate, and therefore we need to use this a lot. Okay, so but what is I? I for the disk, as long as it was passing through the center, what is the I? Remember, moment of inertia passing through the center is how much? mr square by 2. So we have already calculated that. 5 into 0.4 into 0.4 by 2. Okay, so if I did this, this is 0.2. This is going to give me 1. So answer is 0.4. That is the moment of inertia passing through the center. But I don't want passing through the center. I want it passing through A. This is the axis. So how, do you know how to go from this axis to this axis? What kind of theorem do we have? Parallel axis theorem. So I passing through A is I passing through the center plus mass into this distance square. Mass into 0.4 into 0.4. Okay. Now this is going to give me 2. So this whole thing is 0.8. 0.4 plus 0.8 is 1.2. So now my axis, about this axis, the moment of inertia is 1.2. So therefore, when I use for kinetic energy, half I omega square. So if you notice this one, this will give me 0.4. Okay. And so it would have been 0.4 into 2, which was 0.8. Whereas now I'm going to get 1.2. So if I did this calculation, I'm going to get 2.4 joules of energy. Much larger amount of energy, same omega. So does it matter where the axis is? Yes, because the moment of inertia will change, and based on the moment of inertia, the kinetic energy will change. So when you're solving problems, it makes a big difference whether this rod was rotating about this end. So this was the axis, so it was rotating about this end, or whether it was rotating about this end, the center. Because if it is rotating about the center, your moment of inertia is going to be much smaller, right? So therefore, we have to be very careful about what is that we are calculating when we are calculating kinetic energy. So I hope this part is clear to everybody. So now let us see how to use this in problems. So now that we know how to calculate kinetic energy, let us see how to apply it to a problem that looks like this. So I have here a weird shaped object. I am telling you its moment of inertia about A is 20 kilogram meter square. Now you should be able to calculate this for regular objects. Obviously for something that looks like this, somebody has to give you the value. But if I gave you the same thing with a rod, you should be able to calculate because you have a formula for it, right? So let us say that I know the moment of inertia is 20. So which then means using the moment of inertia and omega, I can calculate kinetic energy. Now if I am going to let this object go from here, you see that it's going to basically end up with a velocity. Why does it have a velocity when it comes there? So I leave it here. Why does it come there with an angular velocity? Why does it have kinetic energy? How did it get it? Because at this point it had potential energy. So the total energy that it had here must be equal to the total energy that it has when it is here, right? So at this point, I am going to look at the situation when this C has come down. Now what is the C? C is the center of mass. Why do I need the center of mass? When earlier we were doing questions on work energy, so if you look at this ball and I ask you, hey, wait a minute, what is its potential energy? What will you say? mgh. But the whole ball you are treating it as a dot, like a point. So if I tell you this point is at this height, let's say this was my zero level and this dot was at this height. Now it's very easy to say that it is mgh because the whole dot has one single height. But obviously this ball has lot more points, right? So will I take the lowest point? Will I take the topmost point? But it really didn't matter because this ball is a very small object. So almost everything is at the same height. But if I took something like this, and this fellow is going from here all the way there, and I'm going to say that the potential energy here is more than the potential energy when it is here. You understand it, but I can say the point A has not changed its height at all, right? Should I take this point's height for potential energy? No, right? Then you can say, well, let me take that point's height, but what is so special about that point? So what point should I take? I should always take the center of mass. Okay, so when you are now doing a bigger object, so for example, instead of something like this, suppose I had an object looking like that, and let us say its center of mass was that point, you should not take this height. You should not take that height. You should take this height. Okay, so this is the center of mass, I'll call it Cm, and so this height, the potential energy from the zero level is mass of this object, g into height above, but height above the zero level of the center of mass, not the bottommost point, not the highest point. Okay, it's a very easy basic idea. Probably you're already doing this. Okay, that's going to be extremely important when we are solving problems. Usually, if I ask you this separately, you'll answer. But when we are solving problems, what happens is if you don't remember consciously that I must take the center of mass for finding potential energy, we may end up taking something else, whatever is convenient. Okay, so in this question right now, I'm going to take this guy and that is the center of mass. I'm telling you that is the center of mass, and the center of mass is, if you look at the distance from A, it is 2 meters, but because it is like that, it is at a height of 1 meter from this line, horizontal line, and I'm going to choose this horizontal line as my zero level. Okay, so now if I took this object and I kept it here, okay, and I let it go, you know that when it comes to this place, it is going to look like this. So let me draw this situation. So this is just an approximate diagram. Okay, so let us say that this was the object. Now you know that at this instant, it has an omega. It is going around like this, it has an omega. At that instant, what was the omega? 0, it was at rest. I am leaving it at rest. So omega naught is 0 radians per second. Now when this whole thing is turning around, if this was my center of mass and that distance was 2, when it comes down, the center of mass will be at a distance of what? 2. Okay, but it will be 2 like this, right? Because the center of mass will come in a circle like that, and so therefore everything is going in circles, including the center of mass. So what will be this height? 2 meters. Is that okay? Whereas in the beginning, this height of the center of mass from the zero level was 1 meter. Now it is 2 meters below. 2 meters below. So let us draw a nice table to see how to solve this problem. Okay. So what we are going to do is we are going to draw what we are going to call the energy table. So I'm going to basically put in a table here. And the basic idea of this is that you are going to use energies to calculate this problem. Now, if you look at the energy for this, there is kinetic energy and potential energy for this big object, and that's it. Okay, so that means I need to worry about two kinds of energies. One is the potential energy and one is the kinetic energy. It's a very simple case. So there is only one big object, so single object, and that's what we are going to do in the beginning. Later on we are going to look at questions which involve more than one object. Okay, but at this point let us just focus on this. So now we have two time instants. This was the initial time and this is the final time. Right? In the initial stage, this is how it looked. Finally, this is how it looks. And the question then is, what are the values for energy in the beginning and in the end? Now you might think, why should I go through all this trouble? Why don't I just do potential energy is equal to kinetic energy? You will find that the table makes things very easy when the problem gets tough. You may think of this as drudgery, lot of work right now, but actually this is going to be extremely useful. So I would suggest strongly that you follow it. Okay, so let us look at this carefully. What is the potential energy in the beginning? That is, this is my zero level. I'm looking at a height of 1 meter above. So mgh. What is m? M is given, it is 3 kg. So m into g, which is 10, into height above, which is 1. This is 1 meter above. Height of what? Not height of the axis, height of the center of mass. Above the zero level, I have chosen the zero level as my axis. I can choose the zero level anywhere I please. I am choosing it at the axis, at the horizontal level of the axis. What is the kinetic energy of this fellow in the beginning? Was it rotating in the beginning? No, I said that I'm going to leave it from rest. So if I'm leaving it from rest, then this is 0. Half I omega square, omega is 0. What about the final potential energy? Well, this whole thing comes down. So that means now it is 2 meters below. So m is 3, g is 10 into minus 2. Why minus 2? You know that you're talking about height above the zero level. This was 1 meter above and this is 2 meters below. So minus 2. Okay. Now, what about the kinetic energy? And that's basically what we have spent so much time already on. So what is the kinetic energy? Half I omega square. Luckily in this problem I is given. It is 20. So half into 20 into omega square. Now I don't know what omega is. I am therefore going to write it as omega. This is the value here at this instant. This is the omega about A. And interestingly, omega it doesn't matter which, about what. Whether you took it about A or whether you took it about the center of mass, you took it about any other point, omega will remain the same. Velocities won't be the same. Omegas will remain the same. So omega is not something that is relative to the axis. Is moment of inertia relative to the axis? Yes. Okay. But is omega relative to the axis? No. Okay. So anyway, so that is the straightforward thing. The moment of inertia about A is already given. So now if I total this up, so this is going to give me my total energy. What is my total energy in the beginning? 30 joules. What is my total energy in the end? What is this? This is minus 60 plus 10 omega square. And now there was no loss of energy when I did this. So when it's coming down like this, the energy at the beginning must be equal to the energy at the end. Okay. Later on when we look at we'll look at a concept video where we are going to look at what happens when you are providing extra energy. It will be called work. Okay. Right now we don't have to worry about that. So if these two are equal, because this is my total in the beginning and that is my total in the end, then this basically goes there. So I have 90 is equal to 10 omega square, or omega is 9, root of 9, which means 3 radians per second. So that means I have computed that this fellow is going to come here and is going to move at 3 radians per second. Let us quickly summarize what we have learnt. Okay. So whenever an object is basically a rigid object like this is let go, So you know that this fellow is going to go around, turn like this, right? So let me draw the diagram here. So if I let this go and I'm going to pivot it, let's say here. So the pivot point is the one where the axis passes through, right? Is this necessarily the center of mass? No, right? The center of mass is somewhere there. For I calculation, for kinetic energy, you need I. So for I calculation, what are we using for I? I about axis, right? But when this thing comes down, look at this. This portion is going to go up and that portion is going to come down. So it's going to look like this. Now, when you're using this, what is coming down? Well, the whole object is coming down, but will I use this distance coming down? No, right? I have to use the fact that the center of mass has come down. So that means I need this. So for calculating potential energy, I should use the center of mass. So let me call this CM, center of mass. Is that clear? So that means we are using two important ideas. One, for axis, for kinetic energy calculation. So let me write this as kinetic energy. So for kinetic energy, you need the I about the axis. For potential energy, you need to calculate it for the center of mass, the height of the center of mass. Now, if in a question, like in this question, if I let it go, I looked at it when the center of mass was vertically below. And many questions that will be the case. But should it always be the case? Like for example, what if I ask you what happens at this point? Why should I always ask what happens there? Suppose I ask what happens at that level, then you're going to have a question where this was the axis and the whole thing looks like this. No big issue. Take the center of mass and look at where is the center of mass in the beginning, initial, and in the end, final. The position of the center of mass, the height of the center of mass matters. Is that clear? Whereas for the axis, of course, the axis hopefully is not moving because we are only talking about a very special case. And the special case is that this is, whatever we have learnt is only valid for fixed axis. There are lots of problems with fixed axis, but this is valid only for fixed axis. So you have to be very clear. So for example, what is it not valid for? Well, if I took this marker pen and I threw it, then this guy is going up and coming back down, and you can think of the axis there. So it's not fixed axis. This formula is not true. Kinetic energy half I omega square, not true for this question because the axis is moving. So it's only true for fixed axis. Now the axis need not pass through the center of mass. It can be here. It's still valid as long as it is fixed. Okay, so there are many problems that will be applicable to. In addition, we are looking at one single rigid body. We are only looking at questions where there is one rigid object at this point. So that means we are not looking at the case that we first saw where there is a disk and two blocks are falling from the disk. We are not looking at that case right now. We'll come to that, but at this point we are only focused on one rigid object. Okay. There is one extra point I want you to keep in mind. Now if I tell you at this position, this was the initial position or this was the initial position and this is the final position or this is the final position, you know the initial and final. But many problems what happens is people don't tell you what is the final position. They'll say I left it like this. Find the maximum angular velocity. Where is the maximum angular velocity? When does that happen? Just by looking at it you can see. When does it have maximum angular velocity? When the center of mass is vertically below the axis. Why is that the case? Because if it was like this, remember when the center of mass is vertically below, that is when the potential energy is the lowest. So if the object was like that, and this was the center of mass, and when the object center of mass comes here, that will be when it is the lowest, because after that what is going to happen? It's going to climb back up again. So this is point where potential energy is the lowest, which means kinetic energy will be the highest, which means angular velocity will be maximum. Now you may think, this is very obvious and easy. For this question it was. Okay, but sometimes it means you have to do your calculations very carefully. For example, if I took this question, now I have two rods that have been connected. We'll be doing this kind of a question. If I let it go from here, and this is the pivot, it is nice and simple. You know that this is, the center of mass is right vertically below, right? You know the center of mass for this system must be somewhere there, and it is vertically below. So you expect that this is when it is going to be the fastest. But suppose I held it here like this. Suppose this was the pivot. I'll just show you what happens? If I let it go, can you see? You can see that when the center of mass is now vertically below, the whole thing does not even look symmetric. Right? So that means you need to know that maximum omega means center of mass is vertically below the pivot or vertically below the axis, and therefore accordingly calculate what the height should be. Okay, so we'll look at questions of that kind. Just want you to keep in mind maximum omega means center of mass vertically below the axis. Okay, so just keep this in mind, because when you look at problems, this will then tell you the final position, because this is telling you what the final position looks like. So I hope the basic idea is clear. So let us basically apply this to a whole bunch of problems. There is no way you're going to learn this without doing a lot of questions. So we are going to look at each example carefully, try the example out before you see the solution, because only by trying very hard, whether you get it right or not wrong does not matter. Trying very hard, you will actually become really good at it. This is a tough topic, but it is something that you can master quite easily if you put in the effort.